Okay, we have learned in the video previously that I have uploaded in the YouTube that I put in the e-learning about the introduction of the spectroscopy. The basic thing about spectroscopy is it is a method that we use to analyze our analyte using spectroscopy method. Spectroscopy is based on what? The word spectrum, right? The light. Okay. So we have the light source. Either our sample or our analyte absorb the light, and we have a detector. The detector will detect how much of the light being absorbed. Okay. So it will represent the concentration. Okay. Qualitatively, okay, it will represent what type of the sample. Okay. The type of the sample. Okay. Represent by what? By the bandwidth. What? Right. At which part of the wavelength it being absorbed. So it is qualitative. And then the quantitative part is how much is being absorbed. So we have two type of analysis using spectroscopy method. Okay. It based on light, absorption or emission of energy in the form of light. Okay, that is a basic thing about spectroscopy. And there are several instruments applying this technique, the spectroscopy technique. We have the first one that I have taught in the video is UV visible instrument. We use the UV visible range of energy of light, okay, to analyze our sample, okay, via the absorption of the of the light, okay, of the light of the at certain wavelength by the analyte, and then we can detect how much it been absorbed at what bandwidth, so we know the type of sample and how much it is, the analyte is contained in the sample. All right. And today we have we will learn now at the second part. We will learn about the second instrument, which is atomic absorption spectroscopy. I will share the slide now. I'll wait for a while. All right. For the second instrument applying this spectroscopy technique, we have atomic absorption spectroscopy. Okay, it is basically applied to analyze metals. Okay, metals analyzed in the sample. Right. So this is chapter 3. Okay, wait. All right. So, analysis of inorganic analytes using spectroscopy-based methods. So, inorganic meaning that we have, if organic, we have a molecule or substance that involving carbons and oxygen and so on. But inorganic, we have metals, nutrients, and so on. So, basically, AAS is applied to analyze metals. Okay. So we will have introduction. We have the first instrument is atomic absorption spectrometry, AAS, and then one of the instruments that also applying this spectroscopy method. We also will learn about AES, atomic emission spectroscopy. Okay. If AAS, the concept of the instrument is that our analyte absorb the light and the being absorbed, it represent the concentration of the sample. But in atomic emission, it will measure how much the energy being emitted by our analyte, okay? Because it undergo from we burn out the sample, okay? We we introduce high energy, for example, flame. We burn the sample, and then the sample will excite. Okay, the atom will excite from ground state to excited state, and then after coming back to from excited state to ground state, okay, the electron, okay, after it being from the excited state come back to the initial state, the ground state, it will emit an amount of energy, a packet of energy. Remember in the previous video I said a photon, okay, a packet of energy that uniquely different, okay, for every element, okay. For example, lead. For lead, it will absorb certain range, okay, of energy with at certain wavelength, okay, and then it will not absorb similar at similar wavelength with another metal such as cadmium and so on. So that's why we can differentiate. Okay, the absorption of the energy is from lead or from cadmium and so on, and how much it the concentration it will represent through the how much of the energy being absorbed or being emitted. Okay, this AAS and AES using the similar concept, which is spectroscopy. The difference is the AAS. The concept is the atom of the element will absorb the energy at certain wavelength. Okay, and for AES, atomic emission, the atom will emit the energy after being excited. Okay, so the detector will measure the emission of the energy. For the AAS, the detector will measure how much the energy from the previous source, okay, from the source of the energy, how much it being absorbed. For atomic emission, do we have a source of energy? Because we just measure emission of the energy from the atom, so we don't have a source of energy in AES. We only have detector. That is the difference. For atomic absorption, we have the source of energy that being emit. Okay, it emits a light. Okay, the energy in the form of light. So we have our sample that being excited. Okay, the sample, the analyte in the sample will absorb certain amount of energy. So the detector will measure how much the energy being absorbed. Okay, because it lost some of energy is lost because it being absorbed by the analyte. So in AES, we don't have a source of energy, source of light, because the AES only measure the emission of energy from the element. Okay, so we have two types. Okay, we have flame AAS, meaning that we use flame to excite the or to burn the sample. Okay, to excite the electron from ground state to excited state. And also we have graphite furnace AAS, and also we have cold vapor AAS and its application. Okay, remember guys. Okay, this is special for today. Our Honorable Associate Professor Dr. Razali Ismail, okay, will organize a training, okay, a basic training for the AAS instrument today at 2 p.m. Okay, as you can see in the slide, I will forward in the WhatsApp group, okay, about the info. For those who are free, please, Dr. Razali, okay, he has retired last month, but we still engage with him because he's an expert in this instrument, this in this field of chemistry. So he will share his knowledge about the atomic absorption spectrometry today at 2 p.m. Okay, I think it's via Webex. Yeah, of course, Webex. Okay, we provide. Okay, I forward in your WhatsApp group. For a while. Okay, guys, you have a class today at 2 p.m.
No, sir.
No, sir.
Okay, if no, please spend your time, because it's very, very hard to have Dr. Razali, because he has already retired, but it is his commitment to organize this training at this evening at 2 p.m. Okay, just okay, 1 hour after our class end. All right, so please, I hope that you can join. Okay, you can have your, you can spend about I think this is about 1 hour or 2 hours. Okay, just listen to what he will share about the instrument. All right. So what is spectroscopy? Back to theory for a while. What is electromagnetic radiation? What is a wavelength? What is energy? What is photon? What is absorption? And what is emission? Okay, just come back to the theory. All right, AAS, this is the image of the instrument. Okay, one day, if you if you can meet face to face, if you come to UTM, I will, for sure, I will bring all of you to know the instrument. Okay, all components similar to UV visible previously, but an extra component for ASA, we have atomizer. Okay, in UV visible, we just put the sample into a cuvette, right? Remember, sample container. Remember the Beer's law? What is Beer's law?
Yes.
A equal
Yes.
to, okay, good. Okay, A equal to what?
Epsilon
Epsilon.
BT.
Epsilon B
BC.
C. So B is the path length, right? And C is what?
Concentration.
Concentration. Yes, good. Okay. So in AAS, we have atomizer. Okay. Why we have atomizer? We go back for the AS name, atomic absorption spectrophotometer. So we have to transform our sample, okay, in the form of atom, okay, free atom. We have to give some, okay, as much as we can, the energy, to make sure that all of our the component of in our sample become atom. Okay, in the atom state. Okay, there we have the electron of the atom will excite. Okay, from the ground state to excited state. So in AAS, we provide the energy. Okay, what kind of energy? We burn the sample using flame and so on. We provide the energy to make sure that our sample become atom. And then when our sample become in atom state, okay, then we provide the energy, okay, from the light source, okay, to measure how much of the remember how much of the atom that for example, we supply the energy similar with the packet of energy of for example, I give you iron, okay, Fe, ferrum, iron. Okay, so this packet of this form of energy, amount of energy, only could be absorbed by iron atom. Okay, so if there are iron atoms in the sample that being excited using flame and so on in the instrument, we call as atomizer. We atomize the sample. Okay, and then if there are iron, only the iron will absorb the energy that we supply from the light source. Okay, and then okay, the iron will the electron in the iron atom will excite from ground state to excited state, okay, from higher state. Okay, then the now we have a detector after this. Okay, at the middle one we have the our atomized sample. Here we have a light source, okay, for certain amount of energy, specifically for iron, for example, and we have a detector. If there are iron, okay, iron atoms in the sample, okay, that absorb the energy that we have provide here, and the electron will become excite from ground state to excited state, okay, the detector will detect the decreasing amount, okay, because of energy that being provided, it will decrease. The detector will detect there are some loss of energy, okay. So it means that in the sample we have iron, okay. The light source, okay, normally we have a hollow cathode lamp. It will provide the energy similar to what we're going to analyze, okay. So we have to change the light every if you want to analyze the iron, we have to put iron light here. If you want to analyze lead, we need to put lead light here, okay. It will provide the amount of energy similar with our analyte that we're going to analyze. For example, I give you iron, okay. Next one, if you want to analyze lead, so we need to put the lead source of light here, and then we burn the sample, okay, using our atomizer, flame, and so on. So it will become atom, and when it absorb, okay. For example, now we want to analyze lead. So if there are lead in the sample that being atomized, okay, the lead will absorb the energy that being provided by the lamp, okay, and the electron will excite from ground state to excited state. Then the detector will detect the loss of energy from the light source, so that the amount of lost energy will represent the what? I want to know either you understand or not. The detector will detect loss of energy, okay. So the loss of energy will represent, please, some volunteer. The loss of energy, for example, now we put lead, okay, the lead light, okay, that provide a wavelength that only lead can absorb the energy. All right. So now in the atomized sample, okay, there are some lead inside the sample, okay. Then the lead absorb the energy then the electron will excite from ground state to excited state, okay. And then the detector will detect a loss of energy because there are lead in the sample that absorb the similar energy with similar wavelength from the light source. So the loss of energy will represent what? Please, someone. So the loss of energy will represent the concentration of the lead. Or previously, I assume iron. If we put iron light and then we analyze the sample, the iron in the sample will absorb the light. The detector will detect the loss of energy from the light source. So there are iron in the sample. Similar with other metals. If you put a light source of lead, okay, if there are loss of energy from the detector will detect loss of energy from the light source because it's absorbed by the sample. So there are lead in the sample, okay. That is the concept of the instrument. We have a light source specific for every type of element, okay. If we put the lead light, okay, that we provide a spectrum of wavelength that is only being absorbed by lead. If we have iron sample in the lead, if we have iron in the sample but without lead, so the detector will detect there are no absorption of the light because every element will absorb certain amount of energy, okay. If the energy provided from the light is specifically for lead, so the iron atom in the sample will not absorb the energy. It is very, we call as very selective, okay. the iron atoms will never absorb the energy, the amount of energy is which is only suitable for lead and other metals. Okay, that is the concept of the instrument, because the amount of energy that being absorbed by every element is different. Okay, for the electrons to excite from ground state to excited state. Can you understand that?
Yes.
All right, those. So the application is atomic spectroscopy is important in the analysis of metals, minerals, nutrient, and toxic substance. Okay, we have a lot of metals in our periodic table, right? Okay. As I told you, the method based on the atomic spectroscopy measures the absorption of radiation by atoms in the gaseous state. Okay, because we burn the sample and we become atomized. Okay, and the second one is atomic emission. Okay, the difference between the AAS and AES is, in the AAS, atomic absorption, we have a light source and then we excite, okay, we atomize the sample, so the sample will become atom, okay, and then the atomized, our analyte, if there are, for example, iron light, if there are iron will absorb the energy. But in the AES, we don't have the light source. There are no light source, okay. We only excite or atomize the sample, okay, and then we have a detector. Okay, when we atomize the sample, okay, the sample we atomize and we'll excite and then also absorb the energy and excite from, for example, the iron excite from ground state to excited state, and then after it's being excited, it will come back again to ground state. The electron will come back again to ground state and will emit a certain amount of energy. So the detector will detect the amount of energy. Okay, the energy that been released by the electron is specifically for different type of metal. Okay, if electron in the iron excite from ground state to excited state, and will after it come back to the ground state, after the electron come back to the ground state for iron, okay, it will release certain amount of energy and the detector will detect. For lead, it will emit certain amount of energy that different from iron, so the detector will detect. So our detector will detect what type of metals inside the sample and how much is the energy being released. Okay, so that it also can be applied to measure metals or any analyzed in the sample, but we don't have the light source. So the difference is the AES, the sensitivity is quite low, so we have to analyze the sample with high concentration of metal so that the detector will detect. If we have a very small amount of analytes in our sample, okay, a low concentration, the detector is not able to detect. Okay, so that AAS is more sensitive. Am I correct? So that a metal with only in low concentration also can be detected by AAS. But for AES, it needs a very high concentration because the detector will detect the emission of the energy. So it need to be very it's difficult for the detector in AES to detect the emission of energy. Instead of the detector in the AAS, it detect how much is the energy being absorbed, energy loss from the light source. Okay, so in AAS it's more sensitive. Okay, we can detect even in a low concentration, but for AES, okay, because the detector detect the emission of the energy from the excited atom of the metals. Okay, so it's quite low sensitivity, so we need a high concentration of sample to use atomic emission spectroscopy. So which one for as you can guess, okay, between AAS and AES, which instrument is more expensive? Your idea? What is your idea?
AAS.
AAS, right? Of course. Okay, because we have a light source, okay, and then the instrument can detect a very at low concentration, so it is more complex as we compare with AES, because AES we don't have a light source, so it only detect the detector only detect the emission of the energy at high concentration. So if we have a low concentration of analyte in a sample, we cannot use AES. So the AAS is more expensive, it's more high-end instrument. Okay, next. Not moving my slide. Sorry. Okay, see there? Okay, in the AAS, atomic absorption spectrometer, we have a source of light, okay, energy in the form of light, okay, and then here is our sample. We burn the sample, okay, there is a pump here to suck the sample to the to the flame. The flame will burn the sample, it will become atomized, right? Atomized. Okay, so the atom of our specific specific metal that similar with the source of the light. For example, we have iron light here. If we have iron here, so the iron will absorb the energy, okay, similar with the light source. So the detector will detect a loss of energy from iron source because it be absorbed by the atom, some of the atom inside the sample. So it will detect some loss. That the loss will represent the concentration of the iron in the sample. Okay. All right. So level of detection, part per million. Okay. Relatively incentive in complete volatilization. Okay. There are some unvolatile atoms in the flame. We assume less than 5%. Okay, and then it is reproducible. Okay, meaning that if we analyze our sample again, it will detect a similar concentration. Okay, and then a very low cost per analysis and rapid. So that is why AAS is more expensive or very more chosen. Okay, this is a well known instrument in the industry instead of AES. Okay, so this is the light source. Okay, we have a different type of light source for every kind of analyte. Okay, this is upside down. This is Pb, okay, lead. This is Cu, copper. Okay, K, potassium. Why is Cr? Cr is for what? I just want to test you. Chromium, good. Okay. All right, and then this is what what is the content in the electrode discharge lamp, the light source. Okay, we have a coil, we have a quartz window. Okay, we have a ceramic holder. Later on, we will learn how the light source will emit will produce a light of unique for every element. We will learn after this. All right. Why my slide is not moving? Okay. All right. And then how about the atomization? How to atomize our sample? Okay. To perform atomic spectroscopy, atoms of the analyte must first be formed, usually in the form of atomic vapor. So please, someone close your mute your microphone. Who's that? Okay. So the atomization process, okay, the process of converting sample, okay. Normally we need to have a solution sample, okay. If we have a solid sample, we need to digest to dissolve. We learn, right, the sample preparation. Okay, so we need to digest or dissolve our sample so it will become in the form of solution. Okay, the atomization is a process of converting the sample, okay, into vapor particles. Okay, individual molecules and individual gases atoms using atomizer. That is the purpose of atomizer in our instrument. Okay, okay, where is our atomizer? Here, that is our atomizer. Okay, so we have our sample here. It will absorb, it will we have a suction pump here. The suction pump will distribute our sample in the atomizer, and the atomizer will burn our sample. Okay, and then our sample will become in the form of atom. Okay, okay, if we have a molecule initially, so our molecule will the molecule in the sample will break into single atom. Okay, and then the single atom will excite. Okay, okay, because it absorbs a lot of amount of energy. Okay, and then the excited state of the molecule of the atoms, okay, will lastly, if it absorb a lot of amount of energy again, after that it will become ion. Okay, sorry, not ion. Okay, M plus. So it will release electron. Okay, so this is the concept of atomizer. Okay, okay, this is the basic concept of our AAS that you need to know. We have our light source. Okay, and here our sample being being pumped into the atomizer, and the sample will become atomized. Okay, here you will see a single dot represent the our atomized sample. And then if there is for example, for the light source is for lead, Pb. If there are lead in the sample, okay, that become atomized, it will absorb the energy from the light source. Okay, and then our detector will detect the loss of energy. So that is the basic concept, right? So how to transfer the sample to the flame? Okay, we have to convert the sample to aerosol form. Okay, or also known as nebulized or aspirate. Okay, and then the removal of solvent. Okay, meaning that if our solvent are water, so the removal of solvent being happen at the flame state, that where the water being what? If you burn the water, what will become? Vaporize, right? Evaporate. Okay, vaporization of sample, okay, from solid to gas, and then atomization of molecule into individual gases atom. Okay, here first stage we have a molecule, and then it will atomize. Okay, it becomes single atom. Okay, it will excite from the atom itself will excite. Okay, the electron will excite from ground state to excited state. Okay, and then if the excited state, okay, come back to the ground state, it will emit the energy. This is for AES. Okay, excited state to ground state, and there's some amount of energy being released, and then this is the AES concept is here. Okay, it will detect the emission of energy. Okay, and after that, if the you know, if the atom absorb a lot more amount of energy, it will become ionized. Okay, the electron will come out from the atoms. All right, we have a single atom burned. Okay, and then from ground state to excited state, okay, it absorbs amount of energy from the light source. Okay, and then the detector will detect loss of energy. Okay, we have two types of atomization of the sample. We have flame. We burn the sample using flame. We have to come out with the flame. We have gas. Okay, normally we use acetylene or we have a nitrous oxide to burn the sample. Method of atomization: is sample solution aspirate into the flame. Okay, and then we have graphite furnace. Graphite furnace is we have a graphite tube, and then we put a small amount of the sample inside the graphite tube, and then we will provide we will heat the sample inside the tube. Okay, the sample solution evaporate and ignite. Okay, so this is the different if we have the sample, if we have sodium in the sample, the flame will come yellow. We have different color of flame for different type of element inside. If we have a lot of potassium in our sample, the flame will become is quite indigo, right? And so on. We have calcium in orange, strontium or lithium, we have red flame. Okay, we have turquoise flame, we have a green flame. Okay, for different type of elements. It's very beautiful. Okay, so this is the flame. This is the real AAS. Here is the suction pump. We have a sample here. Okay, this is the flame. We have atomizer. We have nebulizer inside here. Then this is the atomizer, the flame. Okay, this is the flame. Where is the light source? Here, the light source is from here. Okay, this is the detector. Okay, if there are similar elements with the light source, absorb the amount of some amount of energy, so the detector will detect loss of energy from the light source. So that is the concentration of every analyte in the sample. It's quite this is the history of AAS. Okay, Alan Walsh, the father of AAS. Okay, this is the laboratory model of AAS 1954. Okay, to eliminate a loss of vapor at the thermal expansion of the gas form. Okay, it's necessary to introduce a sample after preheating of cuvette, but how? This is the idea, right, of the first AAS. Okay, and the problem is the need in atomization technique to ensure the complete vaporization of a sample, atomizing and holding it within a limited furnace volume. This is the basic theory. So this is the graphite furnace of AAS. Why we need graphite furnace of AAS? Okay. Sometimes our sample contains an element that when we atomize the element, it will evaporate very fast. For example, we have arsenic. Okay, we have what more? We have antimony. When we burn directly into the flame, it will not absorb the energy from the light source because it easily evaporate out. Okay, so we need to contain the sample in a small tube so that it will not evaporate out. Okay, so we need a graphite furnace here. We need a small amount of sample. It will burn. Okay, surrounding by heat. Okay, it will vaporize inside the tube, so it will not come out. Okay, if we use flame, okay, use normal flame, the some of the elements that are easily evaporate will come up to from outside of the flame. If you have light source here, the detector is here. Okay, the atom, okay, the atomized element is easily going out from the flame. it will not, have enough time to absorb the energy from the light source, so that the detector will not detect, perfectly how much of the element inside, because it's evaporate outside the flame. So the solution is we need to have a graphite furnace. So that we burn the sample. Okay, the analyte that contains, the analyte from the element that is easily evaporate, it will not easily come out from the area that we need to analyze the element, because this is the optical path, this is light source. Okay, so we need the elements that easily evaporate to just be in here. Okay, not come out from the area of detection. So if you use flame, the area of detection is open, right? So the elements that easily evaporate, they cannot stay longer in the flame. They evaporate out. So our detector cannot detect the element, because it is not, it's not enough time for the elements to absorb the light from the light source. It will evaporate out. So we need to put, a special technique, so that we need to contain the element that easily evaporate, so that we can detect a more intensity of the light that we absorb. Okay, so that is the purpose. What is the example of the elements that easily evaporate out when we burn? It's like arsenic, antimony. Okay, what else? Okay, or maybe lead. Okay, so it is more, it's more accurate to detect, or to analyze the elements not using the flame. Okay, atomizer, we have different type. We have flames and we have graphite furnace. So graphite furnace is better, but it's quite expensive. Okay, the flame is replaced by an electrically heated graphite tube. A few microliters of sample is placed in the tube. Okay, it is dried and etched at lower heat and then vaporized at high temperature. Okay, the atomization efficiency is greater than for a flame, and detection limits are lower. Meaning that if the detection limits are lower, we can detect at a very low concentration. Okay, guys, I think that's all for today. Okay, and then I need you to listen to Dr. Azali this evening at 2 p.m. so that we can, you can learn. I also will be there to, in the WebEx, to listen to Dr. Azali. So I hope all of you can attend. Okay, can you attend? Okay, test one. You have a question about test one. Okay, actually, we need to do test one, and I think it will. I will give the test. This is week 6, right?
Yes.
Okay. Before the mid-sem break, I think in week 8, I will organize the test one. Okay. Is it okay for you?
Okay, sir.
All right. I need all of you to attend this evening class, this evening, open class about the AAS. I hope so that all of you can attend, because Dr. Azali is very expert in the instrument. Okay. So that's all for today. And see you this evening at 2 p.m. I will be there also. All right.
Bro, we get the attendance.
All right. I will give the attendance again. Okay. Okay. And assalamualaikum and a very good afternoon. See you this evening, right? See you this afternoon at 2 p.m.
Thank you, Doctor.
All right. Most welcome.
Okay.